Today we want to talk about stoichiometry, and stoichiometry is a way of calculating amounts of substances that are formed in a chemical reaction. When we deal with a balanced chemical equation, which we must have in order for us to be able to do a stoichiometry problem, then we can tell a lot of things about the reaction based on this balanced equation. We can talk about the number of particles that are involved. We can say that there are 2 nitrogen atoms that react with 3 hydrogen diatomic molecules, but that's going to end up giving us 6 hydrogens. And on the other side, we see that we have 2 ammonia molecules, which consist of 2 nitrogen atoms and 6 hydrogen atoms. Again, balanced chemical equation, the number of particles on both sides must be equal. We've talked about that before when we were balancing chemical equations in the first place. It also gives us a number of moles involved, and I will say that's probably the most important thing we'll talk about today because that's what we're going to use. This relationship is what we're going to use with stoichiometry problems. We have 1 mole of nitrogen reacted with 3 moles of hydrogen, and when we get done, we have 2 moles of NH3 that are formed, and that relationship of moles is very important. We can also talk about the mass of the substances involved. Well, if we are talking about 1 mole of nitrogen, 3 moles of hydrogen, and 2 moles of NH3, we know that each of our hydrogen atoms is 14.01 grams per mole. We know that each of our hydrogen atoms is 1.01 grams per mole. So if we have 1 diatomic nitrogen, then that means that we are going to have 1 times 28.02 grams per mole for the whole diatomic nitrogen molecule. If each hydrogen is 1.01, we're going to have 3 times 2.02 grams per mole for the entire amount of hydrogen that's involved. And that's going to total out to be 34.08 grams of reactants involved in this chemical reaction. Now, when we react to this, law of conservation of mass says we better have exactly the same amount. And of course, if the particles are the same, we're going to have the same amount. Remember, our nitrogen is 14.01 grams per mole, our hydrogen 1.01. So if we have 3 of those hydrogens added to our nitrogen, we're going to end up with 17.04 grams per mole total for our ammonia, which is going to give us our 34.08 grams per mole. Must be equal. Now, as far as the volume of the substances, when we talk about volume, this can only be used if we're dealing with a gaseous equation. If and only if everything in the equation, the reaction is a gas. We can also say that 1 liter, and we'll learn more about why we can do this later when we talk about gas laws, but 1 liter of our nitrogen gas combined with 3 liters of our hydrogen gas, when it's combined and those are all combined into larger molecules, they will actually end up taking up less space, 2 liters of ammonia. So those are the things that we can tell from a balanced chemical equation. And stoichiometry again talks about calculating how much of the reactants, how much of the products that we would form in specific chemical reactions. So let's take this first example. The first thing I'm going to ask you to do is to make sure and underline what you're given and circle what you're trying to find, just like we've always done. We're looking for moles of ammonia. We're given 1.75 moles of hydrogen. Now, what we're going to do with this is to label it on our balanced chemical equation, and this is how it's going to look. We're going to put the fact that we know there's 1.75 moles of hydrogen. We're going to put the 1.75 moles right above the hydrogen. We are going to then put the fact that we're looking for X moles of ammonia. Sorry, I almost put it over the wrong thing. we're looking for X moles of ammonia. And so those are the two things that we're dealing with in this equation. And I'm going to X out anything else that's in the equation that I'm not going to deal with. And I'm going to underline those coefficients. Now notice, not a single thing that I've done so far is in green. So everything must be done. And what I'm going to do now is to set up what's called a mole ratio for this equation. And the mole ratio is going to look like this. It's going to say, I'm just going to use the 2 that I have dealt with, the 3 moles. I'm going to do it in different color because those are the 2 numbers that we're going to use in our mole ratio. And our mole ratio is going to look like this. It's going to say that there are 3 moles of hydrogen for every 2 moles of ammonia. And we're going to flip that. 2 moles of ammonia, I'm almost running out of room, over 3 moles of hydrogen. That's what our mole ratio looks like. And notice where I put it. I put it at the end of the problem. Okay, so make sure that you've got your mole ratio in there. The next thing I'm going to do is to start the problem with the only thing that I was given in our original problem, the thing that I underlined, which is the 1.75 moles of hydrogen. I'm going to put that over 1 like we've always done. And then the rule in stoichiometry is to use the mole ratio as soon as we can. And on these problems that we're going to do today for this first day, we are going to be able to use our mole ratio for our very next step. Now remember, what I want to do is to get moles of H2 to cancel, bringing back our math, moles of H2 to cancel, so I want moles of H2 on the bottom, which means I'm going to be using this conversion factor, the 3 moles of H2 on the bottom. Almost wrote that again. 3 moles of H2 on the bottom, the 2 moles of NH3 on top. That's going to cancel my moles of H2, leave me with moles of NH3. And when I multiply and divide this together, looks like I'm going to need 3 sig figs. Remember, the 2 and the 3 don't count because they're counting numbers. They're exact numbers, infinite sig figs. So 3 sig figs tells me that my answer is going to be 1.17 when it's rounded correctly, times 10 to the 0. Now remember, I told you that now we're going to be able, if it's times 10 to the 0, simply be able to write 1.17 moles of NH3. Since we don't need to move the decimal, it's already in the correct position, our power of 10 is 0. So the answer to this problem is 1.17 moles of NH3. One more example, just to make sure we've got it. We're going to do the same thing we did above. We're going to circle what we're trying to find, underline what we're given, and 8.25 moles of acetylene gas. You may not know what acetylene gas is, but by process of elimination, it's not oxygen, not CO2, carbon dioxide, and not water, so it must be C2H2, 8.25 moles. Looks like we're looking for moles of oxygen, so that's going to be our X. And we're going to X out anything else that is involved, and we're going to underline our coefficients so that we can use those to make our mole ratio. Now, I really don't have the room at the end of this example problem to put it at the end of the written problem, but as long as it's up here to the right of the problem and not down in our calculation work. I never want to see mole ratios down here. So make sure it's over to the right and up high. I'm going to write that there are 2 moles of C2H2 for every 5 moles. Make sure you write moles of O2 and 5 moles O2 for every 2 moles of C2H2. Starting my problem then with what I underlined, I have 8.25 moles of acetylene gas, C2H2. And one thing you might consider doing once you make your mole ratio, mark out those numbers because you can try to use them later in ways they're not supposed to be used. They're only supposed to be used for the mole ratio, so you might want to consider marking them out. So 8.25 moles of C2H2 over 1. That's how we're always going to start the problems. Now remember, I want to make sure that I am canceling out or reducing to 1 my moles of C2H2. So those are going to go on the bottom. So it looks like the mole ratio that I need to use is this mole ratio, the one that has the 2 moles of C2H2 on the bottom with the 5 moles of O2 on top. That's going to cancel moles of C2H2, and I'll be left with moles of oxygen. When I multiply this out, once again, it looks like I'm going to need 3 sig figs because of that given value. And when I take 8.25 times 5 divided by 2, I'm going to end up with 2.06 times 10 to the first moles of O2. Make sure it's in scientific notation and 3 sig figs when you get this answer. And that's stoichiometry mole-mole calculations.